statistics of something digitalized, right? The propagation delays, the speed, then the power dissipation, and we also talk about those noise margin, right? We have high level noise margin and the low level noise margin, and also we talk a little bit about the power supply, right? For the TTL, we have two different kind of technology. One is the TTL technology, another is the CMOS technology. So we have TTL technologies and we have these CMOS technologies, and they have different power supply. For TTL, we usually use 5 volt, but for the CMOS, we have different 3.3 volt, 7.8 volt, I think 2.2 volt, something like that. So a different power supply voltages for the CMOS technology. Okay. So, and again, then we found that in the TTL loading, we can call it a driver circuit. That means the TTL circuit, the gate, will drive number of another input types. And if there are the logic in high state, so we call it a TTL driving gate. In case of TTL, we call it TTL as a driving gate. That means when it is in a driving gate, it will be source current to the load, right? Source current to the load. Or it can be a sink current from the load when it is in the low state. When it is in high state, it will be act like a source current to the load. When it is at a low state, it will be the current sink current from the load. Sink current from the load. And once again, we have this one for the CMOS. It is like a source and the sink as well. So depending on that, how many loads we are connected here, for example, so this is the gauge. How many load we are connected, or how many gates we are connected at the output of the logic gates. Depending on that, we can increase the number of current here, right? So here, what we can say, like this, you can say, yeah. So when the logic output is high, when the logic output of the logic gate is high, VOH, then we will have a high output current, IOH. And then if we connect some load, that means this is a logic gate. For example, if we, just for an example, if we use two different gates, one is the OR gate, two input OR gate, and then we connected it to a NOR gate. So when the logic gate, or this logic gate output is high, VOH, my output is also high. This is output current. So we are talking about the current of the logic gates. So current of logic gates. So when output voltage is high, we have output high current. Okay. Then that means if we connect more input, more logic gates or more load, whatever we say, they have different names. We can call it a load, we can call it a gate. So if we can improve this gate, that means this is IIH, this is IIH, this is IIH, right? That means if we keep increasing the load or the logic gates, the amount of this current will increase. So IOH, because IOH is now 3 times of IIH. Right? 3 times of IIH, because we connect 3 load. So this is the current. So here it is acting like a source of current. On the other hand, if the output of the logic gate is low, output of this logic gate, output voltage on the logic gate is low, the output current will also be low. When output current is low, that means at that time the current will sink from the load. Current will sink from the load. So here, if we keep increasing the load or gauge, then IOL also increase. So here we can see we have two current, right? IOH and IOL. IOH and IOL. So here when it will be synced, this is IIL, and IIL. So it will, in both sides, if you keep increasing your number of gates or loads, this kind of increase. So, but important thing is that when the output of the logic gate is high output voltage, we can source as a current. We call it IOH, output high, IOH. So that means current flowing out of the logic gate, current flowing out from the logic gate when the output voltage is high or the logic 1. Output high means logic 1. Okay? Okay. And when IOL is my output current low or current flowing into the output pin. Current flowing into the output pin, because this is my output pin of that going. Current flowing into the output pin when the logic is zero. Logic low or logic gate is zero. Okay. So if we keep increasing, this all will also increase. Okay. So this is all about current at the output side. Okay, output high and output low. Now we see. So two current. So same way in the input side we have two current. One is IIH, another is IIL. So whenever we have input current IIH, that means here so this is input current high, IIH. So that means whenever the input is fed into the next gate or the load gate, when the current is high, we call it input high current. And for the load current, during this sync, it will be the low current, right? So IIH. So IIH current flowing into the input of the logic gate when the input of the logic gate is logic 1. So that means whenever we can create logic 1, then it can give some high current. But whenever we have a logic 0, it will actually be opposite. That means it is also IIL. So we have IIL and IOL. So these are the four current parameters we have. Okay. From here, we already get the important parameter, this is fan out and fan in, right? So fan out and fan in have two states. One is low state fan out and high state fan out. Low state fan out and high state fan out. One is high state fan out. Another is low state fan out. So another important thing that IOH maximum or IOL minimum, this will be given in the data sheet. That means how much current it can provide or how much current it can sink, it will be provided in the data sheet. And according to that value, we can actually decide how many gate we can drive at the output side. How many gate we can drive at the output side. So the twisted fan out we already discussed in our last lectures, fan out. So in the higher state fan out, it is actually IOH by IIH. Right? IOH by IIH. Because we have this one, for example, when VOH, we will get IOH. At that time, input is IIH. 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 That is when logic is 1. So we give it a ratio of IOH by IIH. So it's source. On the other hand, when it's logic low, 0, it will be VOL. So we will get IOL, and here it will be IIL. That means sinking, right? So it is known as lowest state. So lowest state will be IOL by IIL. So these are the value is given. So this is fan out and fan in. Okay. So why we just talk about this one? So today we'll try to do some examples. So this is the we already discussed in our last lecture, but still I want to give you some information. So we already discussed. Another important parameter we discussed in our last class about the noise margin, right? We have also high state noise margin and the low state noise margin. And those noise margin came from the input voltage supply, right? From the CMOS and MOS will divide. So for the logic, so this is logic 0, this is logic 1. To have a logic 1, we should have the mean, right? Here, the mean or VOL minimum. What you mentioned, VOL minimum, right? The power supply. Do I have this one today?
VOH minimum.
Sorry. So it will be V input. So if this is input side, so V in, right? Maximum for logic 0. And this one is V in minimum for logic high. On the output side, we have VOH maximum and V input output low minimum. So this is the gap of noise margin, and here, sorry, this will be a little bit upper. So this is the noise margin. So this is high state noise margin, this is the low state noise margin. For high state noise margin, VNH or VHN is equals to VOH output high minus input high, and for low state noise margin, it is input low maximum minus output low. Right? Okay. So today we'll talk about VOH minus VIH. VOH minus VIH. Yes, you're right. And I want to make sure that my equation is okay. So today we'll talk about this circuit, how we can design those circuits by using the transistor and the resistor, right, as I mentioned. So this is all about we discussed from our previous lecture. Now we'll continue with this today's lecture. At first we'll design the RTL circuit to get a logic gate of NOT gate and the NOR gate. Before moving to that, as we will use the transistor, just for recap, in the transistor we know we have 3 different regions, right? One is active region, one is saturation region, one is cutoff region. So usually we use a common emitter transistor. We use a common emitter transistor. This is the symbol of a common emitter transistor. And here we have a base terminal, we have collector terminal, and we have emitter terminal. We give our input to the base terminal, and we take our output from the collector terminal. And we apply some VCC, the bias voltage here. This is the transistor. Whenever we also have to apply some bias voltage here, and we usually use NPN transistor. So this is the bias voltage. So whenever both the bias and forward bias, the transistor will at saturation level. When my input voltage, input side, base emitter junction is in forward bias and collector emitter junction in reverse bias, it is in active region. So if you want to use your transistor as an amplifier, we put an active region. But here we are talking about the digital electronics. We want to use our transistor as a switching. So it can be either in saturation region or it will be in cutoff region. So the cutoff region means when both the bias are in reverse bias. That means if you connect this P side with the N side and N side with the P side, then it will be in reverse bias. So whenever we have in reverse bias, there will be no current, IB will be zero, because to turn on, for example, if it is a silicon-based transistor, it requires either 0.7 volt or some book they mention 0.6 volt. So if you apply 0 here, it will not turn on, will not get IB. And if you not get IB equals to 0, if IB equals to 0, then IC is also 0. Right? So this is the current gain factor beta. Beta value can be 40 to 400. So, but we don't need to bother because IB is still 0, IC is to 0. So that means this is in cutoff region. Cutoff region. Okay? So when you want to reverse bias. And if you apply both in the forward bias, that means if you apply both the sides of the forward bias and you just give the higher potential here, then this potential, this is also become forward bias. It will be in saturation region. Okay? That will be in saturation region. So if we have the characteristics curve, these are the some characteristics curve of this common emitter configuration, right? This is output voltage VCE, this is output current IC. This small region is my cutoff region. Well, there is no current. We can see some small current. This is a reverse saturation current. Okay, this is negligible amount of reverse saturation current, but we call it cutoff region. Okay, and this portion is our actually saturation region. In case of saturation region, we will get a small amount of output voltage VCE. Output voltage VCE, this one. VCE is this one, not this one. This is my bias voltage, okay? So sometimes you get confused. You just think about this is a bias voltage. This is not the, this is the bias voltage. This is not the output voltage. Output voltage with respect to collector, with respect to the emitter, VCE. Here, in case of saturation region, we will get a very small amount of voltage. Usually, it is 0.2 volt. So this is a saturation voltage. To turn on the transistor, as we just mentioned, we just take that it is a silicon-based transistor. So VBE is equals to 0.7 volt or 0.6 volt. Okay, like this. And what else we have? So in the cutoff region, VBE should be less than 0, right? In the cutoff region, VBE should be less than this 0.6 volt. That's why it's cut off. So we will not get any current. And okay, so these are the things we need to understand to move forward about the transistor. So some recap of the transistor. We usually use the common emitter transistor because in a common emitter transistor we can have the current gain, right? We don't have any current gain for the common base transistor. Okay. Now at first we will look at the first logic family that includes the resistor and the transistor in IC. That means we are trying to design an integrated circuit In the integrated circuit, we are trying to design NAND gate, NOR gate, AND gate, any of the logic gates, right? Mostly we focus on two universal gates, right? NAND gate and NOR gate. Because once we have these two gates, we can do any of the binary functions. So before going to this NAND and NOR gate, we will start with a very simple gate, and we design this IC with the RTL circuit, resistor, transistor, logic. This is known as RTL circuit. So here we have two components, one will be the resistor, another will be the transistor. So as I already mentioned about the transistor, we will use the common emitter transistor, and we have to put it in the saturation region, so then we have bias voltage, bias resistance, and we have to apply some current here. Okay. So that means if we have this transistor, for example, so we have just applied some bias voltage here. So we have to give our input signal here, the logic, right? We have to give the logic signal. So logic either 0 or we have logic 1. Okay, so whenever we give some logic 0, that means maybe we are giving 0.2 volt or 0.3 volt or 0. Something, or it is connected to the ground. But to turn on, we know at least we need 0.6 volt. So it will not turn on. Or we can give logic 1. Logic 1 can be 3.8 volt, 5 volt, something else. Any of the, depending on the TTL families, the CMOS families, depending on that, we can decide these things. So then it will be more than 0.6 volt or 0.7 volt. It will turn on, we'll get IB, we'll get IC. Okay. So let's design the circuit of the RTL circuit. In the RTL circuit, we will have a resistor here. This is the biasing resistor, and this is the biasing voltage, VCC. We have a biasing resistor, RC. This is RB, because this is a collector terminal. This is the base terminal. This is the emitter terminal. Emitter terminal is connected to the ground. In the base terminal, we have a base resistance, the biasing resistance, then a biasing resistance, RC here. And we give our input here. And give our input here. Okay. So this is known as the simple RTL circuit is known as RTL NOR gate. RTL NOR gate. So if we have the NOR gate, if we have input here, A is my input and Y is my output, for example. If we give 0 in the NOR gate, we should get output high, right? And if the input is 1, output should be low. This is the logic NOR gate. Now we have to see that whether this circuit performs in the similar way or not. So usually logical NOT gate, this is the logic NOT gate. If you give 1, it will produce 1. If you give 0, it will produce 1, right? So let's see. So when the input signal is 0, the transistor will be in cutoff region. When the transistor is in cutoff region, that means my collector and emitter terminal, this is become open, right? This to become open. So output will come from VCC. The output will be just here, right? The output we can write down some IC times RC. So we get high. Now, if you give the input equals to 1, logic high. So logic high means 3 volt, 3.3 volt, 5 volt, whatever it is. It is more than 0.6 volt here or 0.7 volt here. So that means it's turned on. So that means it goes to the saturation level. We already have given this VCC some voltage forward bias. Okay? And now we are giving the forward bias here as well. So both bias is now in forward bias. And whenever we say that, whenever it is in saturation region, the output voltage VCE is equal to 0.2. That means now this is connected. So now you have to connect the output with respect to ground. So you have to take the output from respective ground means we will get 0.2 volt. So 0.2 is. So this is the very simplest circuit of RTL family. We can design and not gate. We can design and not gate. Now how we can design this NOR gate? Because we have to design any of the universal gate, either NAND gate or NOR gate, right? NAND gate or NOR gate. So in the NAND and NOR input, we have two inputs. So we have to have design RTL NAND gate or RTL NOR gate by using two such circuit. So let's see with the RTL NOR gate. RTL NOR gate. OR plus NOT, right? NOT. NOT means OR plus NOT. This one, right? And so here we have two inputs, A and B. This is my output. So A, B, Y. So as there are two inputs, we have four combinations. So if it is an OR operation, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. That is an OR gate, so it will become opposite. So it will be 1, 0, 0, 0. So you have to make sure that if you can design such a circuit, it will be the same operation. So we have to design with an RTL circuit. We can design like this. This is my DCC biasing voltage. This is my RC biasing resistance. We have RB. We have RB. So we have two transistors here, Q1 and Q2. We give one input A here. We can give input B here or vice versa. Don't worry. And we take output where? We just take output. So the emitter terminal is connected to the ground. The collector terminal is connected to the VCC through this RC. We take the output from the collector terminal. We give our input to the base terminal. So this is a common emitter configuration. So as we have two inputs, now we have two transistors. Previously we saw that we just designed a NOT gate. In the NOT gate we just have one input, right? So that's why we just use one transistor. If you have more input, you have to connect more transistors in parallel. They are connected in parallel, right? They are connected in parallel. If you look at this point and this point, they are connected in parallel. Now see the operation. At first, if you put 0, 0, that means logic 0 here, logic 0 here. So when you put 0, that means either 0.2, 0.3 or 0 volt connected to the ground, this transistor will remain off.
Here on space station.
This transistor will remain off. Similarly, as you give input to the 0 here, this transistor will remain off here. Both the transistors remain off cut-off situation. So it will be open. So we get output from the VCC. We get the output high. Very simple. Now if you could give this logic 1 here and logic 0 here, or 0, 1, whatever it is, they will same. So whenever you get this logic 1, this transistor will turn on. Right? It will turn on. It will become on and it will become off. One of the transistors is turned on. So whenever one of the transistor is on, the collector to emitter junction is now connected. So the current will pass through here and go to the ground. So we know that whenever transistor is in saturation, output voltage is 0.2 volt. So we get the output with respect to ground 0.2 volt in 0. Okay? Or you just think like this. So they are connected in parallel to resistor. So if this becomes open, current will pass through this one. If this is open, current passes through this one. Either path is open other coil is short, current will flow, and the transistor will remain on, so that we get output voltage depending on this amount of voltage, saturation voltage 0.2. So in both case 0 and 1, 0, we get 0. And definitely whenever we have both input is 0, both transistor is now on, and we get output voltage according to this VCE 0.2. So we can design RTL NOR gate by using, you can design this NOR gate by using this resistor transistor circuit. Can you design the RTL NAND gate by yourself? Try RTL NAND gate. RTL NAND gate. How you can design RTL NAND gate?
NAND gate.
Yeah, this is RTL NOR gate.
NOR gate.
Right? I am asking you how you can design RTL NAND gate.
Then we need to connect them in series.
Yeah, that's why I'm asking. I just want to know everyone agree? If you connect this RTL in series, we can design the NAND gate, right? So you have to connect RTL in series. Okay.
I have a question.
Yes.
If this is connected, oh.
So that means you have to connect.
Oh. Yeah.
Like this. Yes.
So isn't two NOR gates also an AND gate?
Yeah, you can do that.
So wouldn't that just double it or no?
No. So you mean, so at first you convert it, then you give invert again and invert it. You want to add a NOT gate.
Like we just drew two in parallel, right, for one NOR gate? We just drew two.
Yeah.
Yeah. And then
So here we just connect two parallel, right? Connected in parallel.
yeah, so that's one NOR gate, right?
Yeah.
So do we have to draw two parallel circuits in series?
So
No.
this is NOT gate. Now this is a NAND gate. This is connected in series. Two transistor connected in series.
Okay, so we don't do two parallels
No.
connected in series, we just
No.
do.
If you want to make it more parallel, what will happen? Actually, you are increasing the number of bits. This is 3-input NAND gate, 3-input NOR gate. If you connect more, it is 4-input NOR gate. Okay. Now this is 2-input NAND gate. If you want to make 3-input NAND gate, you have to connect more, like this. So what will happen? Look at here. If I draw more properly, so this is input A, then this is input B, then this is input C, sorry, it will be in the same page, so like this. So Q1, Q2, Q3. And we should take the output from where? We should take output from the top of the collector terminal. Now here you give input A, B, C. Look at here. So for the NAND gate, what will happen? Just opposite, right? The NAND gate, the truth table of the NAND gate is an AND plus OR. So if it's an AND plus OR, that means this is the AND gate, 2-input AND gate. Or if you want to design 3-input AND gate, so similarly, so then we have to add some NOT gate. This is my NAND gate, right? So in the NAND gate, it will be just opposite. That means whenever we have 0, 0, it will be 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. This is the NAND gate, truth table of NAND gate. So if you just look at here, just don't make it complicated. At first we see with the two input. So 0, 0, 0, 0. When you give to the logical 0 to the input, this transistor is off. This transistor is also off, right? Because you give 0. So if this is off and this is off, so we'll get the output high. Of course, I should have a bias resistance here, RC, BCC. So output is high. Okay? When any input is high, it will get high, because if it is 1, when if it is 0, still we cannot connect to the ground, because this is a series connection, so we will get output high. If it is 0, it is 1, it will be on, but it is off, it still not connected. But when both our input is high, both the transistors start on, then the current will pass through, reach to the ground, will get 0.2. Okay? Or we can, as they are connected in series, 0.2 plus 0.2, 0.4 is still low voltage, logic 0. Because we already see the supply voltage, we can consider logic 0 from 0 to 0.8 volt or usually 0.8 volt to 1 volt. So still it will be logical 0. So this is how we can use resistor transistor to design both NAND gate and NOR gate. So if you want to design NAND gate, you have to connect in series. If you want to design NOR gate, you have to connect in parallel. If the number of input increases, you have to input the number of transistors increases.
So why do we need the resistors though? Wouldn't it work just the same?
So this is the biasing resistor, because it's a transistor. So whenever, if you can remember from the analog electronics class, so you have to bias the circuit, right? So you have to have some certain voltages, so that you don't allow some more current through those transistors. If some excess current comes, it can damage your transistor.
Okay.
And you have to apply this VCE. Whenever you connect the VCE is equals to VCC minus ICRC, right? So these are known as biasing resistor. So bias this circuit. Okay. But there are some disadvantage. Of course, we don't use now anymore this RTL circuit, but this is a very beginning, a very standard one. So the disadvantage are they have very lower noise margin. Very lower noise margin. We already see the noise margin. We have two different kind of noise margin, right? High state noise margin and the low state noise margin. Those noise margin is very minimal in case of RTL. This is the first disadvantage. The second disadvantage is they have low fan out. That means you cannot connect the maximum number of output or the load to the output of the gate. So the fan out is very minimal. And also the speed is very low. Why? Because this resistor. Because this resistor and because they have the low speed. And also they have high power consumption. Because this resistor, they have also the power consumption is very high. So how we can improve this one? So we can improve this one if we can design this one by using diode and transistor. This is known as DTL, diode transistor logic. Diode transistor logic. Okay. Now we move for the diode transistor logic. DTL. In short, we call it DTL. So far we discuss RTL. Now we will discuss DTL. Okay. So if you want to use only a diode at first, by using a diode, we can design an AND gate, right? By designing a diode, So AND gate is 2 input, right? In the AND gate we have 2 inputs minimum. So we have 2 diodes connected, and for suppose some resistance here, we just connect VCC here. This is an AND gate, right? This is an AND gate. Is it okay? So if you 0 here, connected to the VCC, so forward bias, right? 0, 0 will be on, so it will be used as an AND gate, the diode. In the previous circuit, we draw an RTL. We draw an RTL circuit as an inverter. Can you remember? At first we draw just a single RTL circuit to get an inverter. So an RTL circuit was something like this, right? So if I just connect a resistor here and connect a transistor here, it's supposed to be give me some same result, right? Because this is an AND gate, then we connect a NOT gate inverter, it will be NAND gate. It's supposed to be NAND gate, right? Usually, if I just think that this is an AND gate, then this is my NOT gate circuit, RTL circuit, so it's supposed to give me a NAND gate. Whether it will work, so this is the VCC again, and we take out our output here. Right. So what is the problem here? I'm coming. So here, usually we give our input logic 0. This is negative side, right? Negative terminal, 0.2, logic 0, yes. Because you already see, whenever we have the VCE logic 0, we got 0.2. That's why you just consider 0.2 here. As this is a silicon-based diode, as I mentioned, we are trying to focus on silicon-based diode and silicon-based transistor, we can say this is 0.7 here. So 0.2 plus 0.7 will get 0.9 here, right? Now to on this transistor, we need only 0.7. So when it will be 0.7, what will happen? The transistor will be turned on. When the transistor is turned on, here we will see VC equals to 0.2 volt, so output will be 0. So this is not true. Because in the NAND gate, when both input is 0, output should be high. So that means we cannot connect this way. So what we can do? We can replace this resistor with a diode. So also from the name, this is a diode transistor logic. We don't use any resistor here, but I just make sure that why we need this diode here. If we have this diode only, we can see that it will not perform as a logical NAND gate. But now here, whenever we have 0.2 and 0.2, logic 0, okay, 0.2, 0.2, and here is the VCC, so it is turned on, okay. Here we have, at this node, we have how much voltage? 0.9. Now, we have to turn on 0.7 here and 0.7 here. How much? 1.4 volt. So, this transistor will not turn on. So, when the transistor will not turn on, you will get the output high. VCC. Yes.
I was going to ask about DTL. Isn't DTL supposed to be diodes and transistors? So resistors replaced by diodes?
Yeah, that's right.
We have resistors.
So this is the biasing resistor. This is the, we don't, if you just think that this is the VCC duet, we can put VCC here. We have diode and transistor, that's it. We have the diode and the transistor. This is the biasing resistor. The main logic is happening here. So as I mentioned, if we don't have diode here at first, that's why I'm starting with the resistor here. Why we cannot have a resistor here? If you have a resistor here, we can see we have a voltage drop 0.2, 0.2, 0.7. So 0.2 plus 0.7, 0.9 at this point. So now if it is a 0.9, you can see a base here, the base of the transistor. To turn on this transistor, we need 0.7. we already have 0.9. So it can turn on. If it is turned on, then output voltage will be 0.2 VCE. So output is 0. But what we are trying to design? We are trying to design DTL NAND gate. So in a NAND gate, when both input is 0, output is supposed to be high.
High.
But output is low
0.
here. That's why you cannot have a resistor here. Now if you put a, instead of resistor, replace this resistor with this diode. Now we see, to turn on this diode, we need 0.7 volt. To turn on this one, we need another 0.7 volt. So in total, we need how much? 1.4 volt. But how much voltage we have here? 0.9. Because 0.2 we have given logic 0, and 0.7, this is a forward bias. So if you replace with this simplified model, we can replace this diode with a voltage source, the turn on voltage Vk. So 0.2 plus 0.7 is 0.9. But we require 1.4. So the transistor will not turn on. So when the transistor will not turn on, we will get the output VCC. So this is the NAND gate. Both input is high. When any input is high, or another input is low, still same. Because this is still forward bias, this is become reverse bias, but still this is forward bias. This one is still forward bias, okay? So if it is this forward bias, 0.2 plus 0.9, so they are in parallel, connected in parallel. So voltage drop is same. Don't get confused with plus this point and this one, okay? So this is 0.2 plus 0.7 is 0.9. They are connected in parallel. Still at this node we have 0.9. So still 0.9 cannot turn on this one. Still we get output high. When both input is high, now both the diode become reverse bias, right? Because this is high means 5 volt. Some positive voltage is connected to the negative terminal of the diode. So both the diode become reverse bias. Right? Are you confused? Are you okay? Everyone? Okay. So they become reverse bias. Now it will go through here. So this is VCC. VCC is more than 3 volt or 2 volt. We apply here. So we got only 1.4 volt. Then it will turn on and it will give it 0 or 0.2, which is equivalent to logic 0. Okay. In some book, in some reference book, you can see they are actually used, instead of one diode, they use 2 diodes. They use 2 diodes. Then to turn on this transistor, we need 0.7 volt, 0.7 volt, 0.7 volt. Total 2.1 volt.
So I know at the beginning we were saying that we don't want to be in the active region, so we don't want one forward bias or one reverse bias. Is that not what's going on from the input side and then the middle bias, where one's forward bias and one's reverse bias?
So that is the transistor, and this is a diode.
Oh,
This is a diode. This is not a transistor.
okay.
Here we have transistor is this side. We just want to turn on it. So whenever we have, this is VCC. So if I draw again, so this is for the my input A, one diode. This is for input B, diode. They are connected in parallel like this. Now we have this one give to the second diode, third diode. Then we give it to our transistor.
Okay, so they're separate entities.
So this VCC already have the forward bias this side. Now we want to make this one also forward bias. Once we make both the forward bias, this diode in saturation region, and once the transistor in saturation region, the VCE will give you 0.2 volt, which is equivalent to logic 0. So to turn on this diode, to turn on this transistor, we need 0.7 volt. Here also we need 0.7 volt because this is a diode. Here we need 0.7 volt. That means whenever this is a connection from VCC, the same VCC, at this point they need 0.7 plus 0.7 plus 0.7. That means at this point we need 2.1 volt from here to ground. And here we just need 0.7 volt. So it will follow the shortest path. If you give 0.2 here, 0.2 here, this diode will turn on whether they go this way, right? The current will always flow to the shortest path. The current will always flow to the shortest path. So current will flow through this way, come to this ground, come to this ground. They will not go there. But if you give the logic high here, logic high, that means they become reverse bias. They become open. So when they become open, then they will go through this way. And when they go through this way, this transistor will turn on because they will become forward bias here. Already we have the forward bias here. So both are forward bias. Now they become to the saturation region. We get the output 0 volt. So we are taking output from here. So either my output with respect from here to ground, with respect to ground, right? If the output is here with respect to ground, we'll get 0.2. If the output is from here to here, we'll get VCC. Logic high. Okay? Everyone? You okay? Any confusion so far? Okay. So this is the DTL NAND gate. So we can also design the DTL NOR gate, by connecting in series.
That's the AND gate, right?
NAND gate.
AND gate?
NAND. DTL NAND gate.
Okay.
So what is the NAND gate? What is the logic? NAND means and then NOT, right?
Yes.
This is NAND. So if you give 0, 0, it will be 0, then it will be 1. If you give 1, 0, it will be 0, then 1. If you give 0, 1, it will be 0, then 1. If you give 1, 1, it will be 1, it will be 0. This is the NAND gate. So whenever we give 0, 0, this diode become forward bias, this two. So forward bias means, so we give 0.2 volt here for the logic 0. So you can replace with the diode with the simplest model, turn on voltage 0.7, 0.7. So 0.2 plus 0.7, 0.9. So as they are connected in parallel, at this node we have 0.9 volt. But to turn on this transistor, we need 0.7 plus 0.7, 2.1 volt. So this transistor is not on. Since the transistor is not on, is off, then we get output equals to VCC, logic high. Okay. So if you want to keep increase the number of bits, we can just connect more diode in that. So this is known as DTL NAND gate. Now we will focus on anything else. Any questions? Now we'll try to find out some calculation of fan out of the RTL circuit and fan out of the DTL circuit. Let me find out. So we already see high state fan out and low state fan out. So I hope you can design anytime. If I ask you in the exam, design the RTL NAND gate or design the RTL NOR gate or the DTL NAND gate, you can design those circuits. So at the beginning of this lecture, we already saw that when we have two current, either output high, output low, input high, input low, right? So if I just keep it designing here, so when output high, logic high, that means it is giving a logic high output, it will give you output high current, right? Then you can connect some gate here, if you can increase the load or number of logic gates here. So these are input high current. Input high current, input high current, right? IOH. When the logic high. When it is logic low, it is sync, right? Output low, that means logic low, 0, so DOL, IOL. Then we can give some fan out, then it is opposite. Input low, right? It is syncing, it is sourcing. So this is high state fan out, this is low state fan out. For high state fan out, we have IOH by IIH. For low state fan out, we have IOL by IIL. Output high by input high, output low by input low. So this is of course the maximum. This is also maximum. Now we want to try to see the fan out for the RTL circuit and fan out for the DTL circuit. Okay. For example, we have a circuit like this. What is this one? RTL circuit, right? RTL circuit. This is NAND gate or NOR gate?
NOR gate.
NOR gate. Okay, fine. Now we want to drive this some load. So we want to connect some load here. So for example, we have to connect some load here. So we connect another NOR gate, right? We take the output and connect another NOR gate. We can connect another NOR gate here. Like this. So we can keep connecting the NOR gate. Right? As we mentioned in our last lecture, that whenever we calculate the fan out or we want to drive some, we will take from the same logic family. So we have a NOR gate. From the output of this NOR gate, first NOR gate, we will connect it two NOR gate more here. And the value of RC and RB is given. We just consider all the value of RC and RB is fixed. So RB 470 ohm, 470 ohm, 470 ohm, 470 ohm, 470, 470. RC are same, 640 ohm for all the cases. And we also consider that they have the same transistor, so their beta value will be the same. Beta value may be 40, 50, whatever it is. So here they mentioned beta equals to 20. So beta value is fixed for all the transistor bit is 20. Okay. So we have to calculate this NOR gate.
I have-
Usually, yes,
What is the beta value?
beta is called current amplification factor
Oh, yeah,
or current gain factor for
Current
common
gain.
emitter configuration. For the common emitter configuration, current gain factor is beta. So this is known as common emitter. We have three different kind of configuration: common emitter, common base, common connector.
Common connector, yeah.
So common base usually have only voltage gain. They don't have any current gain. For the common base, that is a current amplification factor or current gain factor is known as alpha, and the value of alpha is less than 1.
Yeah.
So if you want to use your transistor as an amplifier, as a current amplifier, we should use common emitter configuration. And for common emitter configuration, beta is the current gain factor, and the value usually we choose 20, usually the beta value more than 40 to 400. So anyway, here we just thought that this is
20.
okay, yeah, 20. So just for an assumption, or we just take that for RTL, lowest voltage to represent input high. For the output RTL, we can write down here, or I should write somewhere here. For the RTL, we just assume that to represent input high, the voltage is 1 volt. Okay? So that means if we have this noise volume, so this is output side, this is my input side, so this is VOH min, this is VIH min, this is VOL max, this is VIL max, this is logic 0, logic 1, logic 1, logic 0. So this is my noise logic. Okay, so they mentioned that for input, for RTL, for logic 1, input high, this is minimum voltage is 1 volt. Okay? Right. So if we look at this 1 volt is minimum, so that means we give 1 volt here. So if you apply KVL here, so we can write down this input high current is equals to I equals to V by R. So we apply some voltage, how much? 1 volt. Then we have to reach to the ground. There is a voltage drop to turn on this transistor, 0.6 or 0.7. They use 0.6 volt here, divided by this resistance, 470 ohm. So it will give you some value, 0.63 milliampere. So we need to find out what? We are trying to find out fan out. IOH by IH. We get IH, input high. For input high, consider 1 volt. So this is IIH. I can write down this. Now we need to find out the IOH, output high. So output high is this way, right? So here, output high of VCC also be given 3.6 volt. So we can say output high. So 3.6 minus 1 divided by 640. Why again 1? Because this output high will give you the input high. We are trying to draw the fan out. Fan out means we need to know how many gates or how many load we can connect to the output of this gate. So to connect output of this gate, to turn on this one, we need at least 1 volt. This is the RTL they mention us. For input high, we need at least 1 volt. So we have to have 1 volt here. So from starting from here, 3.6 minus 1 volt divided by 640 ohm. So it will give you how much? It will give you 4.06 milliampere. So fan out is 4.06 divided by 0.63 which is equals to 6.44. That means we can connect 6 RTL here. 6 NOR gate here. Because whenever we give this IOH, there is IIH, right? Now you can connect each IIH required how much? 0.63 milliampere. And they can produce maximum how much? 4.06 milliampere. So that means we can connect 6 NOR gate here. So this is the panel. Of course, in the data sheet, they will mention the maximum output current. Otherwise, it will damage your this logic gate. So they will mention this. If they mention you cannot drive more than 5 milliampere current or 6 milliampere current, for example, still we cannot connect more RTL, NOR gate. So this is how we can calculate the fan out, right? Okay. If we want ask you to calculate high output voltage of 2 input RTL NOR gate for fan out of 5. That means they already mentioned the fan out is 5. That means we have 5 such NOR gate here. But they ask you to calculate the high voltage or output high voltage. So how we can calculate those things? So the same circuit, we already get the fan out, right? Fan out is 6. So fan out is 6, of course, we take some assumption. We take assumption is 1 volt, we assumption some 470, 640. These are the biasing resistance, right? We have taken that out. So to calculate this output voltage, maximum output voltage, what you need to do, we need to apply some KVL here. So the first KVL we have to apply here. The first KVL starting from the VCC, 3.6 volt minus 640 times IOH minus VOH is equals to 0. This volt minus voltage drop across this resistance. So we have a current here, IOH, right? We already got IOH. Few moments back we got it, times RC. Then the voltage drop, of course, we already mentioned, whenever we'll get IOH, we'll get VOH. So it's a VOH equals to 0. This is my KVL. So what is my IOH? IOH, we can write down, they have given the fan out is 5. So IOH equals to 5 times of IIH. So we can write down 3.6 volt minus 640 times 5 into IIH minus VOH equals to 0. So we can say VOH is equals to, VOH plus this, if you multiply, it will be 3200. IIH is equals to 3.6 volt. Say this is equation number 1. We have to apply another KVL at the output side because this output node, we just can apply KVL from here to here. We have to apply another KVL from here to here because this is connected. So we can write down this KVL, VOH, starting from VOH, so this is VOH. VOH minus 470 IIH minus 0.7 equals to 0. So VOH, so 470, as I mentioned, all the resistors value are same, still is the 470 ohm, times IIH, because the input current, the output current IOH is now IIH for the input current for this load or gate. So VOH minus 470 times IIH minus VCE minus 0.7, this voltage drop to the ground. So starting from here, we'll reach to the ground. This is the KVL we apply now. Another KVL we apply starting from here we reach to here. So we have VOH, VOH, we have IIH, we have IIH, we have some value, constant value, there's some constant value. This is equation 1, this is equation 2. So if you solve this equation 1 and equation 2, you will get IIH value. So IIH value is something 0.79 milliampere. So they ask us to find out the output voltage. So VOH will be IIH. So if you put them any of the equation here or here and solve the equation 1 or equation 2, you will get the output voltage VOH. And VOH is equals to 1.07 volt. So this is how we can solve, we can calculate all the values. We can calculate the fan out values, we can calculate the output voltage, and input voltage is given. And still I have time. Should I continue one more example for the DTL? Hmm? You are already exhausted? Okay. You get it? You have any questions with that one? Is it okay? So during the exam you have to solve these things. I'll give you the equation, I'll give you the questions, mention the RB value, RC value, the beta value. You have to calculate this input voltage, output voltage, the fan out, like this. And also in exam you have to, I'll ask you to design 3 input NAND gate with RTL, 3 input NOR gate with DTL, something like this. Okay?
Don't make it too big.
Yeah?
Don't make it too big because
No,
it takes a time to draw
Yeah,
this up.
I will make sure not to read. Okay, so we'll continue on Thursday, right?
We can draw. Drawing is fun, but if it becomes too big, it consumes a lot of time.
Yeah, I will make sure not to read.